Hello AP Physics 1 students, welcome to Simple Harmonic Motion. What we just saw were guitar string vibrations, and we could visualize them because of the strobe effect due to a camera. Here is a tuning fork vibrating in slow motion. Here's a cymbal being struck. Now, what do a cymbal and a tuning fork and guitar strings all have in common? Well, they're all musical instruments of some variety or another. But what I'm more interested in is their vibration. All of these things vibrate, like your vocal cords, like the leaves and limbs in a tree and a breeze, like your car when it hits a bump, it vibrates. And to understand this motion, we have to understand physics. We have to understand equilibrium and restoring forces in kinematics and energy. In this video, we're going to continue our attack on mechanics, and we're going to talk about kinematics and all the other things that are wrapped up in this vibration, this oscillating motion. We're going to strip it down as simple as it can possibly be, and that's called simple harmonic motion. Whenever you have something that is vibrating or oscillating in any way, then you want to employ the tools of simple harmonic motion on the AP test. Now, we're going to strip this down to its most basic, simplest, like the name implies, simple harmonic motion, simplest characteristics. And so we're going to look at two types of motion, or two types of objects that you'll need to understand for the AP test. They are springs or masses attached to springs as they oscillate back and forth, and a pendulum as it oscillates back and forth. Okay? So first key important thing to understand is that whenever we have something that's vibrating or oscillating, there has to be an equilibrium position, a position where it will be at rest and stay at rest. So like for this spring over here on the right, then this center spot right here this is the unstretched position of the spring. If I push it to the right, then the spring pushes it back towards this equilibrium position. If I pull it to the left, then the spring pulls it back to this equilibrium position. So this B and D position are the equilibrium positions where the force from the spring would be zero. And so if we leave it there, it would stay. But if we put it in any other position, off towards A or to the left towards C, it will be pushed or pulled back to equilibrium. For a pendulum, this is also true. So the basic position, the equilibrium position for a pendulum is in the full down position, where gravity's down and tension is up, the forces cancel, and so therefore it can sit there and not move. If you displace it to the right, then it will be pulled back by a component of gravity. If you pull it to the left, it'll be pushed back to the right by a part of gravity. This is key, that you must identify where is the equilibrium position, because that's where all the forces cancel out. Now, the end points where it's oscillating to the right and to the left, like here from A to C and back to E, which is the same as A, then those are the amplitude positions, where it goes maximum to the right or to the left. Or in our pendulum, here is our maximum point or amplitude position to the right and left as it swings back and forth. So this pendulum would be like someone swinging on a swing. So here are the key things that we need to know about these points. You have to identify at the maximum amplitude, which would be points A, C, and E. A and E are max to the right, C is max to the left, that the net force is at its greatest amount because the spring is pushing or pulling the most. And therefore, we have our maximum acceleration at that point because the force is the greatest there. This is our max amplitude position. Now, at the max amplitude position, the velocity will be zero because it has gone back and forth, and then when it's at the end, it's stopped. All right? So the equilibrium position is in the middle And that's the point where the acceleration is 0 because the net force is 0. But the velocity will be at a maximum because the forces, say from the spring, push it towards this equilibrium position, and at that spot the forces stop pushing and it has inertia, so it overshoots and goes through, and then the spring starts to pull it back. So the central position or the equilibrium position is the maximum velocity position. So the kinematics graphs are kind of complicated. So they are all oscillating like sine and cosine waves. Okay, so like here's this black one is the displacement. So when the displacement is here, 0 at equilibrium, that's where the velocity will be at its maximum right here. And then they oscillate back and forth. So I'm going to show you some simulations of this because it's pretty hard to tell just from looking at this graph what's going on. But I want you to understand that they're all oscillating in sine and cosine waves, and they're all offset. They're all what we call phase shift, 90 degrees. And then there's energy going on here. So if you look at the spring, when it's completely at its maximum compression or maximum stretch of the spring, you have maximum spring potential energy. But it stopped moving, so there's no kinetic. But when you're in the center, where you have your maximum velocity, you'll have all kinetic and no potential because the spring is no longer compressed or stretched. The same thing would be true for the pendulum, except this time, instead of oscillating between spring potential and kinetic, you're oscillating between gravitational potential and kinetic, and gravitational potential and kinetic, back and forth. Okay? So we're going to go through these in a simulation as well. The last thing that we need to know about simple harmonic motion is that there's a time period equation. The time period for a spring is down here. It's 2 pi square root of m over k. I want you to note that for a spring, when it oscillates back and forth, that how much mass you put on it makes a difference. More mass, more time period. More time period means it takes more time to go back and forth. So remember, that means the frequency is smaller because time period equals 1 over the frequency. But if the spring is springier, if you have a higher spring constant or force constant spring, then it will vibrate faster back and forth. Okay? For a pendulum, notice that it's 2 pi square root of L. L is the length of the pendulum, over G, which is the gravitational field strength of the Earth or the acceleration caused by gravity. Notice that the length matters. The longer the length, because it's in the numerator down here, then the greater the time period. If you wanted to double the time period, you'd have to quadruple the length because it's square rooted. So 4 times the length, square root of 4 is 2, twice the time period. Now, for a spring, if you doubled the mass and you double the spring constant, that's a 2 over 2, that would cancel, and you'd have the exact same time period. So let's look at some simulations. So here we have a mass attached to the end of a spring. And it's on a frictionless surface of science, so it's going to oscillate forever. All it does is go back and forth and back and forth. Let's take a look at the time period first. Okay, so if we start out here at our max position and it's going to go out and back, if I hit run, notice how long it takes to go back and forth. Okay, so now if I make this farther, you would think that it would take longer to go back and forth. And it does go faster in the middle. But the time it takes to go all the way back and forth doesn't matter, because our time period equation is, time period for a spring is 2 pi square root of m over k. So the mass and the spring constant matter. So if I make this distance really tiny, it will still take the same amount of time. It's just going to move really slow because the spring is stretched much less. All right, so let's take it back to where we were. And now let's show that the mass matters. If we take more mass off of this thing, make it about half the mass it was before, it should run faster. Because as the mass goes down, the time period should also go down. It's in the numerator. make it even smaller, it should run much faster. And it does. Spring constant's in the denominator. So what we do to the spring constant will have the opposite effect. So if I make the spring constant smaller, the time period will get larger. So it should run slower now. And if I make the spring constant really high, then it should go, the time period should go down, which would make it run faster. And it does. Now let's take a look at a simulation for a pendulum. So here I have two different pendulums. I'm going to move one of them out to 20 degrees to the left and another 20 degrees to the right, so they're the same. And if I hit run, one's got more mass than the other one. You would expect that maybe they would take different time periods, but their time periods are exactly the same. Because remember, the time period equation for a pendulum oscillator is 2 pi square root of L over G. So the length of the pendulum matters and the gravitational field strength matters, but the mass doesn't matter. And actually the angle doesn't matter. So let's prove that. So I'm going to take this one out to say 15 degrees. I'm going to take this one out to only 5 degrees. And you can see that they take the exact same amount of time. Let's take a look at the length. I'm going to move this one out to, move this one out to 20, and I'll move this one out to 20 as well. And I will make the length of the red one half of the other one. And so it should go faster, because as the length goes down, the time period should go down, which means less time to go back and forth. And that is true. All right, now let's take a look at all the kinematics, position, velocity, acceleration, and the energy, potential, and kinetic as a function of time. I'm going to pause it here at the end to get us right to the end. So I want you to notice when we're at maximum amplitude, we have 0 velocity because it has to stop at the end. But we have maximum negative acceleration because the spring is pulling us back to equilibrium. When we're at maximum amplitude, we've stopped, so therefore the kinetic energy is 0, and we have maximum spring stretch, so we have maximum spring potential energy. Now, at the equilibrium position, I want you to notice that the position is 0 and the acceleration is 0 because the spring is no longer stretched. But we have our maximum velocity, so therefore we have maximum kinetic energy, and we have 0 gravitational potential energy. Another way to look at these energy graphs is if we look at them relative to position. So you can see that as we oscillate from our maximum to minimum positions, that our potential and kinetic energies oscillate back and forth from maximum to minimum, but they always add up to the total same maximum amount of mechanical energy, as long as there's no friction. What happens if the spring is vertical and the mass is oscillating up and down? Let's take a look. Now, in this case, we have the same sort of oscillation up and down. The time period would be exactly the same as before. Time period for a spring is 2 pi square root of m over k. Now, over here you can see our energy graphs are a little bit more complicated. So I'm going to slow this down so we can take a look. Notice that we have kinetic energy, we have gravitational potential energy, and we have elastic potential energy. Key thing to remember, kinetic energy is always still going to be maximum at the equilibrium and 0 when it stops at the ends. Gravitational potential is the same as before, mgh or mg delta y. Here's our 0 height, so the higher up it goes, the more gravitational potential energy it has. And then our elastic potential energy or spring potential energy depends on the stretch or compression of the spring. The more it stretches, more potential energy. But even though we have 3 energies now, it doesn't matter. Our energy over here total remains the same as long as there's no friction. Here's our pendulum again. Let's take a look at the energy related to a pendulum. Notice it just swings back and forth. We're going from kinetic energy here at the bottom to gravitational potential energy here at the end. And it's just oscillating back and forth between the two. The maximum potential energy equals the maximum kinetic energy as we oscillate back and forth. Now let's take a look at the velocity and acceleration vectors for a pendulum. So let's start with the velocity vector. And notice it was 0 when we started. It's maximum at the bottom. It's 0 at the end. And it's always tangent to the pathway we're taking. Our acceleration vector is a bit more complicated. So I want you to notice that we have multiple forces acting on this pendulum. So out here at the end, we have a tension that's up towards the center, and we have a gravity force down. The gravity force down and an upward part of the tension cancel, and so we have only a portion of the tension pulling it this way, so it's going to accelerate in the direction of the path. But as the pendulum moves, we get to the bottom down here, and at the very bottom, the tension is the only force up, gravity is the only force down. Tension is greater than gravity because we're moving in a circle, and so we have a centripetal acceleration here. So we're moving from a tangential acceleration here to tangential and centripetal to only centripetal at the bottom. It's actually kind of complicated. Let's look at one last simulation. So in this one, we have a mass that's going to oscillate back and forth, and then another mass is going to collide with it. In this case, the mass is going to be dropped on it when it's at the very end of its motion. Now notice that the mass drops on when this 1 kilogram mass was stopped. So it didn't lose any energy. The original energy was 0.005 joules. The final energy is 0.005 joules. However, since we now have more mass, the time period has increased. The amplitude is still the same because we haven't lost any energy. So the spring potential energy is the same, so we have to go to the same x location. Remember, the spring potential energy is 1/2 kx squared, so it doesn't matter what the mass is. And so our velocity will have to go down because we have more mass, therefore less velocity to keep the same kinetic energy. Now, let's drop the mass when it's at the center. This time the mass is moving when the 2 kilogram mass is dropped on top of it. When that happens, I want you to notice that that is an inelastic collision, a completely or perfectly inelastic collision. So kinetic energy is lost. We started with 0.005 joules. This time at the end we have less mechanical energy. Since we have less mechanical energy, the masses can't go out as far anymore because spring potential energy is 1/2 kx squared. We've lost energy in the collision, so therefore we have less amplitude. Our velocity is also decreased because this was an inelastic collision where mass was added, kinetic energy is lost, so the velocity goes down and our amplitude is less. Now, College Board likes to have these questions where they group different parts of physics together. So we're going to work some sample problems, and one of them will be where we have a mass on the end of a spring and another mass comes along and hits it, and they link together and then oscillate. Until then, see you next time.